So welcome back. Welcome to another video on TOSBIS GG128 Engineering Calculus 2 video. And we'll be beginning the first section today. We said we split it into three sections and we'll be looking at the introduction to the integral calculus. So we want to derive our understanding of integral calculus. And just like what we did, or what should have been done with the differential calculus being derived from the tangent problem, we want to see how we're going to derive the area problem from the integral calculus from the area problem. So what do we mean when we say the area problem? Okay, so what we mean by this simply is just what is the area under this curve? That's just it. What is the area under this curve? If we shade the area here, what is this area between? Let me give it from point A. Let me shorten it here so that it cannot just be from the origin, just should I from any point. So if we shorten this now and we take this down to mean A and let here mean B. So from here to here, what is the area under this curve? And quickly, I like, okay, it's simply, and you might stop, you might get stuck. What is the area under this curve? Take a moment to think about it. Well, if you think about it for a moment, the natural thing you begin to ask yourself is, okay, what is an area? How do we calculate areas normally? Yes, from primary school and all of that, you've been told the area of a rectangle is length times breadth for a square, and all of that. But now, if we're going to generate the area for a curve, let's go back to all of that. How did we get the area for those common shapes we're used to? Well, if we think about it for a moment, what we just realize is that the area of any straight line shape like this, right, is always just equal to the base, the length of the base multiplied by the length of the height, and that's just it. So for a square where all of it is the lengths are equal, it is not equal, but just pretend it is. It will just be having the length of the base L multiplied by the length of the height, which is L. So we're having L squared. For a rectangle, we know that the length, if we call the length of the base L and the height, let me just use B, and the height H or L, whatever you want to call it, we know that the area is going to be the height multiplied by the base. Okay, so or the length times breadth as might be used to. Then when we go into a triangle, we realize that well, a triangle is just, you can say it's just the half of a rectangle. So if this is the base and this is the height, well, the triangle will be h times the base multiplied by half, since it's cut into two, and we get our half times base times our height. Okay. So that means we just need to do the base multiplied by the height. So okay, so good enough. The base is b minus a. But what is the height? Well, the height is constantly changing. Why did we not have this as a problem here before? The reason why we didn't have it as a problem with all the shapes is because they were straight lines, if you think about it. So the heights were constant. So the height was constant during that time period. But for a curve, the height is not constant. So how do we now give the area under the curve? Right, and you might be wondering, why are we so bothered about this? Well, if you look at all the applications that you've done by knowing how to calculate the areas of all these common shapes, you understand that it's very important. So when we go into the areas under our functions, which is very important, we'll also want to have a way of understanding how to calculate the area of the curve. And this will even lead to the distance problem, as we'll see, which is a major application of always having the area under a curve. So what do we do from here? Well, we say, okay, since the height is constant, it is constantly changing. Does this mean that we can, well, I think the smartest thing, or what the mathematicians thought of, was that, okay, we can approximate this area by using rectangular. Basically, we can use, from what we've been our, childish techniques in primary school or whatever, if we have a composite shape, right, we can break it into similar shapes. So if we have a curve here that we say the height is constantly changing, why don't we just, use stripes? So like, for instance, we know that, okay, if we can put this as a stripe, let me use a different color so that the point comes out as well as I want it to. So let's say I have a stripe, I have a stripe, I have a stripe. We can tell, okay, so this is the area, right? Each of these heights with the thickness can be calculated, which would just be the rectangles, like small rectangles, just small rectangles that we know we can calculate. The lines already have thickness. I just want you to see that the line itself has thickness. So if we can use enough number of lines, right, we can tell the area of this curve, because each line, making it small enough that, since we know, for this is what I mean, so we just get the idea out. So if I have a curve, if I can just take a portion here where a very small portion where the height, I can assume that the height is constant during that period, and I take my strip there, I can calculate the area of this strip. You do it for another small section, on that small section where the height stay constant. Okay, and then we can get the area. So how do we write that algebraically? Well, let me go back from all of this. Let me go back from all of this and let's build up from here. So what this means is we can, so what I'm saying now is that we can approximate the area from A to B using what? Rectangles, really. So we can say rectangle. So if I call this x0, which is where my A is starting from, x1, x2, let me put x3, x4, x5, and my B, let that be equal to x6. So I can say I can approximate the area with strips like this, right? So between x2 and x3, I can have something like this. Between x3 and x4, I can have something like this. Okay. Anybody who has gone over the notes will know that I'm purposely being a bit wrong, with a bit inconsistent. We'll go from there. Okay, so I can do something like this, right? Just something like this to approximate the area under the curve. And this is fairly okay, right? Because the area of the rectangles are sort of equal to the area under the curve, except if you just ignore some of the minor details. But for our work, we'll not ignore anything. But we can say that this is an approximation, right? Where we can say that the width of each of the rectangles is equal to delta x. So we have delta x's, delta x's, delta x's. Okay. So what this means is that we can say that the area under the curve can be approximated using the areas of each of the rectangles. And what can we say is the area of each of these rectangles? Well, we can say this one, if we make all the widths the same, I can say it's just equal to delta x multiplied by, okay, let me not factorize already. So I can say it is equal to the x0, or x1 minus x0, let me even say that they are the same at the moment, up onto the function at x sub naught, or the function that we're taking of the rectangle, the height of the rectangle. Then, okay, so let me this for now. Let's take our time to introduce the concept. So we're having x1 minus x0, then multiply by the height of the first rectangle. Let me denote that by h1. And I can say the next one is going to be x2 minus x1 multiplied by h1 plus x3 minus x2 multiplied by h2, and all the way plus, then all the way to xn minus xn minus 1 multiplied by hn. Sorry, that should be okay, this 2, this 3, so this should be hn. So we can say that the area is equal to this, right? So that the area can be approximated by this, not necessarily being equal to it. But what we now want to do is, okay, this is a bit messy. We want to find out, is there a way we can express this compactly? Is there a way we can actually write out the h1s, h2, h3 in terms of the parameters given? Just calling it h1 isn't very nice. It doesn't really relate to the parameters that we've given here of x and f of x. So we want to change that. That's just what we want to see here. But I want to fundamentally first understand that the area of the rectangle under can be approximated using the length of the rectangles, and that's just it. So each of these just represents the area of each of the rectangles, and that is what we have. Okay, so moving on, how do we now represent our h's in terms of the parameters given to us? We don't want to write it as h1 because h1 is just what we put up. Let the height be h1. But how can we represent it in terms of the quantities we have? Well, this is where we come up with the issue of left endpoints and right endpoints, or sample points in general. And that will come up next time. So at this moment, we'll be able to introduce the area problem, see what it is, why we need to solve the area problem. And we have some sort of starting point now, which is use of rectangles to approximate the area under the curve. But how to accurately, or will I say effectively do that, is what we want to come up with. We'll be looking at that in the next video.